Okay, so let's get started. Hello, everyone, and welcome to our cyber training webinar. And so today I'm so honored to have Professor Tao Cheng to join us to give us a talk on the topic of space-time AI for humanitarian aid, disaster relief, and infrastructure resilience. So Professor Tao Cheng is a professor in the Geoinformatics in the Department of Civil, Environmental, and Geomatic Engineering at University College London. So she serves as a theme lead for mobility at the Alan Turing Institute and is a member of the College of Expert for the Department for Transport at UK. So she's also a founder and director of UCL SpaceTimeLab. So it's a very well-known SpaceTimeLab to gain actionable insights and knowledge from spatial temporal data. So her research is very much focused on space-time. So her research interests span AI and big data network complexity and urban analytics with applications in transport and mobility, safety and security, business intelligence, and natural hazards prevention. So she has secured more than 25 million pounds. Wow, this is a lot. In research grants in the UK and the EU, and she has collaborated with government and industrial partners in UK, and also including the Transport for London and London Metropolitan Police Service and Public Health England, and also Arup, among others. And she has published over 300 research articles and received many international received many international best paper awards. She is also our team member for our cyber training project, and she's very valuable people for our project. I'm so honored to have her. So now let's give our warmest welcome to Professor Tao Cheng to give us this talk. Thank you, Tao.
Thanks, Zhe. Thank you very much for the warm welcome. It's a great honor to be on this project. Thank you for bringing me in this because this is the area I think I was so passionate about because the natural hazard and the infrastructure all related to everyone's life. So for this talk, I try to use this title to wrap up our work in this domain. So I think it's very important to somehow to reflect where we come from, and also to say how we address those problems. So I want to share a little bit about my lab. As Zhe mentioned, we are SpaceTimeLab. So we do data. Okay, the data is basically, maybe I can minimize this. The data we all have is really spatial and temporal. So really, as I said, our work has been around prediction, profiling, simulation, and visualization. So our research theme actually is covering transport, mobility, crime safety, business intelligence, and environment resilience and public health. I think for today's talk, I'm going to be more focused on the environment resilience and the public health. Somehow they all related to also transport and crime and security. So how I'm going to conduct today's talk, I want to reflect on how we start with integrated spatial temporal modeling to what we are right now, spatial temporal generative AI, how we can do this, use all the tools we have from step to where we allow and apply them in the domains we're going to talk about here today. This is 4 cases I think I'm going to use in the talk. So before I go that, I want to mention a little bit to say the approach we're taking is integrate the space and time. And we use network-based approach because especially for urban studies, people really working or moving around the networks. So we use network-based approach. And since we allow in the AI and more generic AI space, so lots of those deep learning approach use graph-based approach. And of course, everything we do right now, all AI enabled. So this is the term I'm going to use when I explain these 4 examples about the fire, landslides, flooding, and the COVID-related study. So I want to start with very early work we've been doing, which is to look at the forest fire in Canada. That's really quite a long time ago. The paper is published in 2008. So now nearly 15 years ago. So at that time, I think it's AI, artificial neural network just started, okay? But lots of the work, because I believe most audience in today's talk are come from spatial domain. So we do lots about spatial analysis. However, lots of the other space, like study electric hazard or study about the transport people, they look a lot about the temporal perspective. So ARIMA is autoregressive integrated moving average model. It's a model for time series analysis. So we propose, say, why not statistical approach can be integrated together with neural network. So we propose, or what they call integrated spatial temporal forest prediction kind of framework to integrate time series with neural network. This is recurrent neural network. It's very early work. I think quite a few people at the time really looking at this. So what we're trying to do is, because when we look at this is annual forest burning area in Canada, and we look at them, they definitely have a temporal trend, right? So that should be a time series. But again, lots of people, if you only use time series alone, but you kind of really lost the connection in spatial domain. So what we're trying to do, bring these 2 aspects together. And then that's why we propose what they call the integrated spatial temporal forest fire prediction. So that's kind of, so in this way, we can really say if we use the ARIMA purely time series, which is something here, and then that's what we proposed is this one, and that's the real data. So kind of say, oh yeah, this looks better than purely use time series, or you only use this one is purely use what they call neural network. So this is a small movement. And then later on, we got a little bit better, say, hey, actually, there's a better model. The model actually is integrated space and time together, which is ST-ARIMA. I don't know if any of you guys are really doing this spatial temporal modeling, use a statistical model. This is called spatial temporal autoregressive integrated moving average, okay? So this one, actually, we are using this to look at the temperature, annual temperature in China. We got about nearly 127 stations. This again is annual temperature. But again, if you look at it, they have very strong temporal trend. And again, they also have very strong spatial autocorrelation. So we think, yeah, maybe we can use ST-ARIMA, which is a model for dealing with correlation in our data, both spatial and temporally. So what we did, this one slightly different. So this is a ARIMA model, which really look at this bit is an autoregressive bit. This is a moving average bit, okay? I mean, I don't think I have time to go through the details, but I really want to say, this is the very first model integrated both spatial temporal dimension together. And the neural network, what the neural network is doing, I know now everyone uses neural network. What the neural network is really doing is really say, hey, there's some trend, like the temporal trend, actually. They're very good to model the, what we could even say long-stational. Long-stational means to say, if you have a different mean, they can handle it better. So we think maybe we can bring these two together. So that's how we did. So what we did is we use ST-RIMA, just purely use the statistical approach, and then we can combine neural network with ST-RIMA. And that's the real data. If you compare the data, you can say, if we can make use best of both the statistical approach and the neural network approach, give you much better result compared with the real data. So how can we really quantify this is better? We look at the residues of the mapping. So this is the residue. So if you look at the residue, this is the ST-RIMA model's residue. You can still see they're very strong spatial patterns there, right? So you can say, you know, this is China, this is warmer, this is cold. And they still have a pattern very strong, but this is a residue. After you're done with the neural network and ST-RIMA, the pattern is less strong as the spatial, as a purely used statistical approach. So what I'm trying to say here, I mean, conventionally people use regression model, then use ARIMA, then we use ST-RIMA, then we trying to make use of neural network. No matter is artificial, is, I mean, ANN is the same. It's, I mean, RNN is one type of ANN, right? But say we can combine them together. So use ANN to look at the trend. Use ST-RIMA to really look at the fine residues remained after we use neural network. So in this way, we improve the modeling. So that's, I hope I give you an example to do that with what I call integrated spatial temporal modeling. Then later on, we move to say, hey, as I said, we are working, we are living in urban. We really work along is around the networks. So this is the project I'm working with Metropolitan Police. So this actually is developed from the work we have done with Transport London that really look at the road network. So what I try to, we do lots of things in this project. So what I want to share with you is to say, what do we do with one of the things I think is relevant to what I'm going to talk about here is we're moving from conventional, this is purely, you may say polygon or regional based approach. We got the hotspot. Then we say, oh, this is a hotspot based on the grades. So this is a two area based approach, grade or polygon based approach to find the hotspot. So what do we do here? We say, can we make the prediction of the hotspot more accurate? So we develop what we call space-time kernel density approach. But more than that, this is a space-time kernel density, but we push it to networks. So this is called network-based kernel density estimation. So in this way, we are able to push the prediction accuracy at the street level. So what's relevant for the topic today? Actually, we did this for crime. Actually, it can be used for traffic incident, can be used to file incident. So that means to say, with network-based approach, we can increase the prediction accuracy, right, to a street level. So now, if we move to deep learning approach, because now everyone knows deep learning. So if we move to deep learning approach, said because the problem of use network-based approach, so this needs to be covered up. This is a kernel. If anyone knows kernel density-based approach, it's a kind of scan in space. So two-dimensional scanning and also temporal scanning. So if you need to find the optimum boundaries of your kernels, you need to scan them, and it's really time consuming, and also sometimes really difficult to get the best result. So because of this, we're thinking, can we use even better tools, which now is network-based or graph-based deep learning. So if we put them into a deep learning problem, So you have to dealing with the data sparsity, because the crime data set or any incident data set as the crime, they are just have a very sparse distribution in space, right? And the same thing if it's traffic incident or it's a fire incident. So they have a sparsity in the temporal domain and also have sparsity in the spatial domain. And then you want to model them around the network topology, right? And if anyone knows that, if anyone doing deep learning, I don't know the audience, I hope there are some people do, you may say, because this is not a balanced regression learning problem. So how we address this problem, we propose to do what we call a gated localized diffusion network. So what does it mean? It means to say, this is the original data set they have input, is your time series. Okay, they have an incident around the networks, use graph structure. And then we use what we call the gated network, which is like that, recurrent neural network. Actually, it's used this gated function to kind of addressing the temporal sparsity. Then for the spatial sparsity, we use what we call localized diffusion network. This is very similar to the network-based kernel density diffusion to deal with the spatial sparsity. Then once we've done that, we can put them together. And then, as I said, we have firstly do the spatial, then the temporal, to combine them together, then we make the prediction. So that's how we address this problem. So we use the real case to test it. So this side, because we can only show you with the open data set, although we have tested in the London Metropolitan Police, we use some file data, use some traffic incident test in China and in London, but we can only show you with the open data set. So here is the result with the algorithm on the South Chicago is open data set. So what is showing here? So we want to say if this deep learning method works better than what we already done with the network-based kernel density and kernel density estimation. So here is our method, the red line. So what does this mean? This is what we call the hit rate. The hit rate means to say, if for hotspot prediction, if I say I want you to give me top 10% hotspot, so you gave them top 10% hotspot, like I'm showing here in this red line, and then how many crime or incident really happened on those hotspots. If all of them on the hotspot, then you got a hit rate of 100%. If you say you only got, say, in his case, if I give you 20% of my hotspot, you only got a 60% really happening on those hotspots. So this is a way to evaluating how effective or how accurate your prediction is. So if we compare these two, both are our algorithm, so we can see the graph deep learning based method works even better than our network-based kernel density. So here shows the result in a graph, in a figure. So look at this. You can follow me, right? So you can see the cursor here at the lower part of this slides. So the green dot means they are on my hotspot. Sorry, can you hear me? The blue point or the points are not precisely on the hotspot. So if you look at this graph, you can see 1, 2, 3, 4, 5, 6, 7, 8 are may not on the whole hotspot, but we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So you may say, yeah. So we got to say 8 out of 22 maybe not on. So equally you may say 16 out of 22 are our hit rate. So it's close to what we said, 60%. So that means the hit rate, okay? So this is just showing, I think, yeah, our result. And this is the network-based kernel density, both are our result, but this is the latest deep learning approach. So this means to say, use deep learning, graph-based deep learning can really push the boundary of sparse data prediction. So this can be used for fire incident and traffic incident. I move very fast. Okay, if it's too fast, you can stop me. Okay. So so after we have done that, so related to natural hazards, I want to give you another example we have been doing is to use support vector machine. I think before graph deep learning come out, I think SVM is very popular approach. So we use it to do quite a few natural hazard study. One is the flooding, one is this landslides. I want to show you this landslides. So this one is a European-wide project, quite a big project. So our task is trying to say, can we map out the vulnerability of landslides based on the historical landslide in the southern Italy. So based on this, we used the random forest to do this. So what do? We use the quite lots of dimensional data set as I showing here about where the landslides have been occurred, what's DAM, what's land cover type, soil type, and also how wet is the surface. So and expect lots of things. That's the information we have. We input in and we use a random forest approach to do the classification. And more than that, we'll not only say, hey, this the area where we have a high vulnerability to landslides, but actually we also can sharing the types of landslides. So that here is the landslides type. So what's the use for that? Because we will know different landslide, different type of landslides, you may need different approach to how to say, to if it happens, you need a different approach to rescue it, or you have a better preparation. So that's one use for this or for that. More than that, we can also see which kind of key infrastructure might be prone to the landslides. So we can evaluate the economic consequence of it. So that's the few slides I want to show you. This is not directly my work, is my colleague's work. It's called the cluster of our lab. Also, my colleague working on the project, my postdoc also contribute to it. So what do we do to do this? So to evaluate the cascading effect. Oh God, that went so fast. Okay, let me go back. Yeah. Oh, why is... No, I had to go back. One moment. Sorry about that. I want to go back. So what do we do? So basically, we first say at this level, with urban level, we have the graphical level, we have the infrastructure level. This layer is input by us, right? And also the water pattern impact also with this key infrastructure. This could be the roads or can be the bridges. So once we've done that, then we can evaluate, say, hey, at the national level, this is the disruption of the scenario, and then you have, say, national level, what is relevant, the whole transport networks can be relevant for it. So this is a little bit of simulation there. Then you can say, hey, how this could be impacted the economics. So this is just show you the outcome. So this would be, say, hey, this is another region called Bologna. So it's in Italy, and then how the GDP might lose after the earthquake. This would be, say, hey, how the earthquake, all the cities may be impacted by it. So this gives you some ideas. Say, hey, it's not only about the natural hazard. It's about, say, if the natural hazard happened, which infrastructure might be affected by it. And then what's the cascading effect might have in terms of the economic cost of this current place, and also the cascading effect to the labor in place. So yeah, there's further models to say, this is use agent-based simulation to understand sorry, why it's so fast, to understand the economic cost largely. Okay, so you can do the simulation of the roads, you can do the simulation of the bridge or the key infrastructures. So that's that for natural hazard, for landslides or key infrastructure. I don't know if anything what you guys are saying in the, okay. Okay, it's fine. Sorry. I'm just looking what these guys saying. So now another thing I want to share with you. So we talk about SpaceTimeAI. I mean, basically deep learning can be used for many things. I want to show you a lot for images or videos has been used hugely for nature hazard related study. So this one just to show you, we use images or use videos to understand the weather and condition. So this one is used one model can really tell you it's day or it's daytime or nighttime, it's clear picture, it's clear, or it's say, the sky is clear or it's raining, snowing or foggy, or all of them. Actually, we call the weather lab. So this can really give you all information. Of course, this is racing also on the image lab approach as well. So this just show you some results here. So you can really tell clearly, what's going on there. So yeah, this is the, downtime is very clear, but low fog, right? This is really raining and foggy. This one is really daytime and low clear, but it's raining weather. And again, so this is really can tell you precisely, all the elements about the weather. So what's the usefulness for this? So what do we do here? Is to really trying to improve our cycling, because I mean, I know we talk about nature hazard, but nature hazard will have an impact on human beings, right? So if right now everyone talk about the decarbonization, and in the UK, we really want the proactive travel, means to say when more people get on their bikes or walking. So for one key issue for the barrier of more people get on their bikes is the safety, because UK don't have the cycling lane as popular as say in Holland. Everyone can get on their bike because of very designed cycling lane, but that's not the case in the UK, although the transport authority try to set up more cycling lane. So how can we use the AI to improve the cycling safety? So that's what we did here. So based on the weather information, and also we use other approach to try to sense what's really around the cycles. So we can really understand if the cycling behavior is safe or not. So that's this paper about. And then I want to show a video. You can be more clear about what I'm talking. It works. Okay, so you can see this is very, very fast real-time processing. So it can automatically detect all the objects around the cyclist, right? And then you can also sense about the objects around the cyclist. So it's, it's building or it's, all the things. So in this way, we can really give an alert to the cyclist, is your behavior really safe or not? So in this way, this is based on the very small devices on the bike. If you pay attention to the flashlight one is the sensor, next to it is the little camera, because light is needed when you're cycling. So the camera mounted on the bike. So it's very easy, a small devices you can mount it on, is very portable devices, and it's real-time processing. So in this way, I hope can improve the cycling safety. So what is the latest? Okay, another one is a camera, just looking at the front. So this is something further development. This is my colleagues work out, is James Harvest. So this is a 600 degrees camera, if you can look at it. So the image is really, again, they're also detecting everything around it, but it's even harder because of the shape of the video coming in. So what are they trying to do now is also trying to use large language models to say, hey, can the images with the text, with everything can be combined together to improve the cycling safety, because this is a student came from Thailand. So in Thailand, lots of this motorbike actually is quite a lot safe. So they further working on that to improve it. So that's that. So I want to also show you, see how this can be used to study about the public health. I mean, as COVID has been passed, this is the work we do with a very big largest project in the UK to study about the virus transmission in the local community. So for this project, we have tracked over for the whole project, we have over 40,000 people join the trial. So basically, they join the trial. They answer lots of personal information. They also been contributing their blood samples to check the effectiveness of the vaccination, and they also voluntarily contribute to be tracked. So at the end, we got up over 10,000 people who has their GPS data set. So we link those data set with their personal social demographics, okay? Because even so, for the whole UK, only got 10,000. We can't really do very fine-scale spatial analysis, but at least we can do the mobility related to social demographics. In this case, it's the age and the income. So from all the we really see from this, for different age. So this is really, say, for example, like here, we talk about, say, how far maximum distance from home, okay? Due to different policy. This is talk about second lockdown. This is a third lockdown. You can say who is most affected by the lockdown. Actually, is for the people age 35, okay? And then look at them, which group they are. So this is talk about the income, okay? So this is lowest the income. Again, in terms of income, is lowest income and the youngest group, actually the most affected. Because we will understand, say, COVID have a strong impact, stronger impact for the transmission, maybe say for the death rate for older people. But for the lockdown policy in the UK, most people are affected, all the young people. Why? And the young and relatively poor people. Why? Because those people don't have a car. So they don't drive around. So they just stay at home. So actually, those people have a quite large of impact in the mental health. So that's probably what we get out of this. Another one is we study about the public sentiment taking COVID. This is use social media data. Again, we use some algorithm to detect the age and the gender, and then to understand, are they really pro vaccination? So our finding really says to say, yes, older people above age 40, they're all pro. Even men is more pro vaccination than women. However, in terms of the sentimentation, actually women are more, how to say, get the what they call to say more supportive than men. So basically, it's just to say, hey, that means to say if we really want to that vaccination to the wider population, so we really should target the age below 18 and in between 18 to 40, because age 40, they're all really positive about the vaccination. I think I will use another 5 or 10 minutes to really 5 minutes to really talk about latest work, which is use the mobile phone GPS data to understand the human mobility. So this is we use the mobile phone data. We can really understand the people's movement, and then we can link up to active travel. We can also use to evaluate the policy impact. This is to talk about in London, we have a low transport neighborhood. So what does it mean to say, hey, we have a set of boundary. If the cars lot belongs to residents here, they cannot pass through this region anymore. So we push the traffic to the side. So this can really useful to evaluate the impact of policies. Okay, so what is latest now? Actually, we can use the data to build up what we call, I think this should be what they call the digital twin. Okay, so digital twin is say this is related to the topic. Say, can we understand the impact of flooding to the whole lateral resilience, to the transport lateral resilience? So, I mean, you guys must know more than me. I mean, in the UK, it's lots of flooding. Okay, and there are some days they've been flooded, the people can't use the road. So this is ongoing project. Basically, we want to develop what we call multimodal, people-centric digital twin. So I think I'm cautious about the time, right? So yeah, basically what we're trying to tackle in this project is to say, we going to move from, we want to build up a dynamic digital twin, and then is cross the flooding with the users, which is basically the data reflected in the mobile phone data set, and this is going to be the multimodal. So basically, this is to say there's a layered the data, and then we put the data into what they call the data engine. This is the fundamental of the digital train bit. But more than that, we want to do simulation and then to really evaluate how resilient the system is. So what's really ready to achieve? I think it's really say, it's not only about the infrastructure, it's really about the human being, right? So return back to this COVID. Another project we are working on is trying to see how we can improve policy making in the COVID. So this is the project we're working on with Singapore government to try to, again, use the mobile phone data set to understand the people's response to policy making, and then learn how we can, based on what already happened, the data, can we improve our decision making. So this is, say, digital twin and the spatial decision making. I think it should be the way we go. So this is use multi-agent reinforcement learning to do that. I'm not going to the detail of it. Okay, if anyone have interest in it, I can answer that. So this is the partners we've been working with is a lot, as you can see, to dealing with natural hazard infrastructure or human beings. We need to have an interdisciplinary cooperation. So this is showing some of the cooperators we have here. And this is my team, so they contribute to my talk. So I acknowledge their contribution. And this is the website of our lab. This is our LinkedIn. So yeah, you can follow us. So I think I stopped here just so we can have a little bit time for Q&A. Thank you very much for your attention.
Thank you. Thank you so much, Tao. So if you have a questions, you can unmute yourself or you can type your question in the chat box. I think one Falia, he said he would like to have the paper link. I think, and I at that time I took notes. I think it's Rosser et al. 2016. So maybe Tao, if you can forward me that.
Yeah. I think in the slides, what the DOI is in the slides. I mean, yeah, you should be able to get that. That's fine.
Okay.
Okay, there's one question on there.
Yeah.
It's
So
geographically balanced trading. Yeah. So I think
so
the
was
question.
geographically imbalanced training dataset ever a prominent issue for the introduced space-time AI project? For example, some regions are underrepresented in economic assessment, in the natural hazards impact, and how it raises any geoethical concerns.
Thank you. It's Junkun, right? Thank you for your question. I think this is a really good question. I think I fully agree, or I do think it is all very important issue we need to address. Okay. For the algorithm itself, is the imbalance training is a problem we need to address. For the ethical issue, I think yes, as well. So does it really raise a geoethnic concern? Yes, if it's underrepresented. But why I say but? Because this question has always been asked when I talk about the crime. Use this as example. People keep on saying, hey, your model couldn't really tackle the situation if no one report crime. I mean, if no one reported, I mean, no matter it's a machine, or no matter it's a policeman, they wouldn't go there. Same thing as natural hazard. If there's no one have ever reported, it's not in your data. If it's not in your data, so that's a big problem, because no matter how good is the model, if the data is not good enough, of course, they will create lots of problems. So that means to say, when we look at it, no matter which algorithm we're using, or we talk about AI, is fundamentally data algorithm, right? Now we talk about the computation resource, then it's the application. So I think all of them are important, but the data is very important because good data, you can use different algorithms to deal with it. But without good data, no matter how good algorithm you have, you will still have problems. Okay, so I think that's my answer for that. Is that okay? That is, I don't know. Does that answer your question, Junquin?
Thank you. Thank you, Tao. I think we have another question. So thanks for your talk, Professor. Could you please explain how you would use digital twin in your research? So he's
Okay.
really interested in this project.
Okay, so for digital twin now, I think it's a buzzword, okay? However, I mean, digital twin is really happening right now. So what we are doing right now, we derive what we call the multimodal traffic flow and to be the input for digital twin of transport for London. So what does it mean? It means to say we got the flow everywhere around the whole network, because right now for Transport London, they may have a good data derived from cameras, but it only have maybe a few hundred. But the whole London network got over 60,000 networks, links. So our data can supplement the data to them. So in this way, they can have what we call real time, real traffic flow in multi-mode. So just this give you one example. I think the currently lots of digital twin is more like representing what is happening right now, which is the very good step, but really to push it further, I hope, just like I presented for the digital twin for the flooding, it's not only just about representing what happened now, what in the past, but really say, can we make use of what we learned in the past to really simulate what might happen if another flooding or another natural disaster happen, like the Halloween you have in America. So can really make a better preparation. So the same as I did say, hey, we try to make a digital twin, maybe say digital twin of human activities. So when next pandemic happens, everyone is better prepared. So that's the reason we are doing digital twin in that sense. Am I answer your question?
Thank you. Yes, Yuhang said yes. And we have another question. So can you share a little bit more about the policy project being undertaken for the Singapore government? It sounds like a novel approach to address policy development, implementation, and evaluation.
Yeah, I think I've already touched this a bit. Yes, so why we're doing this? Because I think during the pandemic, it's lots of people say we do simulation, right? I mean, there's lots of model has been developed to estimating how many people will be affected, how many people will die. Most of the time, they over exaggerate the numbers. So what we're trying to do here, because we have a very detailed behavior data set, so we try to say push the prediction a little bit more accurate, use real data with real network to really simulate the situation more close to reality. So we hope that in this way, we can make the prediction more accurate, and also since we can predict the situation and we can validate it with real data, then we can really provide a scenario test for the policymaker. So in this way, I hope they can really help them to do decision making. So that's what the development, implementation, and the evaluation. We use the real data to do the development. We use the real data to do the evaluation. Am I answer your question?
Yes. Oh, we got another. So thank you for your excellent presentation. So as for your public sentiment and the Vesne project, you mentioned that you applied some algorithm to identify the age and gender info from the social media data. So however, as far as I know, many social media data won't use user profile info. So could you please go into more detail on how you retrieve this information? Also, many aged people may not use social media, and how do you handle the data bias issues?
Okay, so thank you for this question. I mean, for social media data, there's a package to do the social media, to analyzing derive the age and the gender from the social media data. Okay, the precise package, I need to go back to check it. I can let you know a little bit later. Okay, if you can write an email to me, I can answer you this. So for the other question about, say, you're right to say aged people will not use social media data. It's absolutely right. Not only aged people, maybe very young people don't use it. But it's not to say because we have less aged people or less young people don't use it, that means that everything we do with social media data is not right. So you have to know the limit. We need to understand this bias in the data. So that's why I always say it's very important. And no matter what we do, we need to know the limitation of our data. So when we make a decision making, you would say, hey, this analysis is based on the limitation of the data, right? No matter it's the mobile phone data I mentioned or social media data we mentioned, they all have a bias in it. How we're dealing with the bias, I think we turn back to the question about the imbalance, the regulation actually is happening a lot when in our analysis as well, because this is also imbalanced learning, because you have a bias in your samples. This is a problem you always have to address. Is it okay?
Thank you. Thank you. I totally agree. And I think I always talk to others and say that even though now we have AI machine learning, but nobody actually can replace human. It's still like we are as human to do the decision. So we analyze data to get better knowledge from data, but that not might be 100% correct. But we just use that information to help us to make a decision. Okay, any other questions?
Yeah, it's good to look
Okay.
so I don't look.
Yeah, if not, so let's give our biggest thanks to Dr. Tao Cheng, and thank you so much for your inspiring talk, and thank you for joining us, and thank you for your time, and also I want to thank everyone for joining us this morning, and so I hope you have a wonderful day or evening if you see in Europe.
Thank you. I think
Okay.
the slide, I think the video has been recorded, right? You should be able to get all the things you needed from the video. If you want me to share the slides, it's also fine. I can share the PDF later. I send it to Ze, and then Ze can share it with the group. For the guy who asked me about this detailed package and to get the age and agenda, write me email. I get that answer for you. Okay. So
Yeah,
thank you
so
so much, Zhe, for the invitation again. Thank you to everyone joining the meeting today. Thanks a lot.
yeah, so our project website is posted in the chat. So this video gonna post it to our website later. Okay, thank you, Tao, and have a great afternoon or evening.
Thanks, everyone. See
Okay,
you guys.
thank you.
Thanks a lot.
Bye.
Yes, bye.
Mhm.